Hi everybody, in this lecture I will show you the definition of a rank of a given matrix as well as the way how we can find the rank of a given arbitrary matrix of size n by n. Okay, saying that, let's start with the simple definition of what a rank is for a given matrix. And here's the definition of the rank of a matrix. Suppose we are given an arbitrary size matrix. In this case, say it's an n by n matrix. Okay, here's what we are given in the beginning. So m is the number of rows and n is the number of columns, and it can take on any values. Okay, and the first thing is that if we after we reduce this matrix into either reduced row echelon form or row echelon form, where this REF in capital letters represent the row echelon form, and whereas RREF represents reduced row echelon form, then rank of matrix A is said to be the number of non-zero rows, or the number of pivots or pivotal positions, or the number of basic columns. Okay, so there's some terminology to talk about before proceeding with the example of how we can find the rank of a given matrix. Here, as we remember, well, first of all, it is arbitrary to reduce our matrix either to row echelon form or reduced row echelon form. In other words, we can use either Gaussian elimination method or Gauss-Jordan method that we already have learned how we can apply. Okay, so after eliminating our matrix or after reducing it to one of these echelon forms, we examine either the number of non-zero rows after we are done with the elimination process, or the number of pivots. We know what a non-zero row is, right? A non-zero row is nothing but a row in the end that have at least one entry which is not equal to 0. So, and the number of pivots is something that we can also use to find the rank of a matrix. Again, after we're done with the elimination process, either by using Gaussian elimination or Gauss-Jordan, we count the number of pivotal elements or the pivotal positions. And what are the pivotal positions? Well, the pivots are the first non-zero elements in each non-zero row. So we look at the non-zero rows and find the very first non-zero element in each non-zero row if there is any of them. Okay, and we count the number of pivots. This is also a possible way to find the rank of a matrix. And another way is the number of basic columns. And the basic column is nothing but a column that contains pivotal positions. So if you call a column a basic column, then it means it contains one of the pivots that we have found after we are done, of course, with the elimination process. Okay, so there are three possible alternatives that we can use to find the rank of a given matrix. And by the way, the concept I will deliberately defer the concept of basic columns to our next lecture. This is actually the topic of our next lecture, which is also an important concept, since we will be using this concept in the solution of homogeneous systems. And homogeneous systems are a special kind of linear systems that needs special treatment for the solution. Okay, so let's make a simple example, and suppose this is the matrix given us. Okay, suppose we are given a 4 by 5 matrix in the beginning, and we are asked to find the rank of A. So we need to compute the rank of this matrix. Okay, then how will I do that? The answer is easy. we need to follow the steps, the basic steps that we have just defined. And what are the specs? What are the steps anyway? So we need to first reduce our matrix. We need to reduce it to either row echelon form by using Gaussian elimination or reduced row echelon form by using Gauss-Jordan. And for the sake of simplicity, I will be using Gaussian elimination, and I will turn this matrix into its row echelon form, and then we will use one of those three possible ways to find the rank of that matrix. Okay, let's start. Okay, what am I gonna do in the first step is that, well, I will use Gaussian elimination. So what should I do? First of all, I start with the very first row at the top and check if the first entry is not equal to 0. If it is not equal to 0, this is the very first pivotal position, right? Because a pivot is nothing but the leading entry in each non-zero row. And by saying leading entry, I mean the very first non-zero element in that row. Okay, in that row, which is not equal to 0. Okay, so and then I will eliminate these values below the pivot position if I'm using Gaussian elimination technique. And how can I do that? You know, by simply performing elementary row operations. I need to replace both row 2, row 3 and row 4 by something else, right? For instance, for the row 2, I should add row 2 minus 2 times row 1, and this would enable me to eliminate this 2 value in which is the first entry of the second row of the given matrix. And for row 3, what should I do? I should replace row 3 by performing again an elementary operation, an elementary row operation, by simply adding row 3 minus 1 times row 1. Okay, and for the row 4, for the fourth row, then I should replace it again by performing some elementary row operation, and in this case I replace row 4 by row 4 plus minus 3 times row 1, right? So after applying this change, the new matrix becomes this. Okay, the first row hasn't changed in the meanwhile because I didn't perform any elementary row operation on that row, but the remaining 3 rows have eliminated their first values. So we got here 0 in the second row, we got 3 minus 1 minus 5 and minus 4, right? And how I obtained these values? I simply multiplied row 1 by minus 2, which means multiplying each entry in row 1 by minus 2, right? Minus 2, 2, minus 2, minus 8, and minus 6. And then added these values to the values in the second row, which yields me the new second row. In other words, the new values in the second row. And for the third and fourth row, now our new values are 0, 3, 0, minus 2, and minus 4. And for the fourth row, I obtained the values 0, 4, minus 4, minus 11, and minus 11 and minus 7. Okay, now below the first pivot element, I eliminated all the values. Now their values turned into zeros. Now the second step is that I will continue this process, right, until I am done with the Gaussian elimination method. In other words, after I reach to a matrix which is in row echelon form. Okay, then what should I do now? I'm done with the first pivot. Now I switch to the second pivot, right? I look at the second row and find if there is a pivot element, and the answer is yes, we have a pivot element right here, which is 3. Why? Because the second row is a non-zero row, and the very first entry from left to right, which is not equal to 0, is 3. So 3 is the new pivot position, and I should eliminate the values below this new pivot positions, right? So the values here I just circled in red should be 0. So how can I do that? Again, I continue the Gaussian elimination method. I need to replace row 3 and row 4 by something else, and this something else is this. I need to replace row 3 by row 3 plus minus 1 row 2, right? Because why is that? Because if I multiply row 2 by minus 1, I get minus 3 right over here, and adding it to the third row, I eliminate 3, right? So it becomes 0. And in the same strategy, right, I replace row 4 by row 4 plus row 4 plus minus 4 over 3 R2. And why I multiplied the second row by minus 4 over 3? Because if I do so, now in the second entry of the second row, I get minus 4. And when I add it to the fourth row, I eliminate the value 4, which becomes 0. So after making these changes, then our new matrix becomes, right, let's write it down again here, right over here. We got 1, minus 1, 1, 4, 3, and for the second row, 0, minus 3, minus 1, minus 5, and minus 4. And for the third row, as desired, I got 2 zeros now, and here is 1, and here is 3, and here is 0. I perform element-wise addition in the associated, right, associated rows. So this is what I'm doing here. So this row again, 0, 0, minus 8 over 3. Yeah, I'm careful about not making a numerical error as well, and this is something I also advise you to do so. Minus 13 over 3 and minus 5 over 3. This is our new matrix. So look at the situation again. Let's examine our new matrix. We have, right, 3 zeros here. Now we got 2 zeros, okay, and the number of zeros, you know, should be strictly increased, right? Should be strictly increased when I move from the top row to the bottom row. And in the first row I get no 0. In the second row I have 1 0. In the third row I have 2 zeros. But in the last row I should have at least 3 zeros to satisfy that rule of the Gaussian elimination process. Now I'm done with the first pivot, I'm done with the second pivot. Now I look at the third non-zero row. Yeah, I'll look at the third row. And what is the leading entry here? Because this would be our new pivot position. And this is the one that I just circled in red. This is 1. So, and I need to eliminate the value below it, right? So minus 8 over 3 should become 0. And how can I do that? It is simple. Just multiply the third row by 8 over 3 and sum the third row with the fourth row. Okay, let's do it. Let's jump into the next step. And here is the thing. Okay, here's the thing, right? So let's do it. I need to replace the fourth row by fourth row plus 8 over 3 times row 3, and our new matrix becomes, let's see what it becomes. We got 1 minus 1, 1, 4 and 3. We have values 0, minus 3, minus 1, minus 5 and minus 4 in the second row, and in the third row there has been no change in the meanwhile. Just write their values as they are in the previous step. What has changed in the meanwhile is the values in the fourth row, right, at the very last row, in other words. So 0, 0. Now we have another 0 over here, 11 over 3. Okay, and minus 5 over 3. And then again, after each elimination process, I check to see if I reach to the row echelon form. Okay, and here in this case, as you notice, you see we have the number of strictly increasing zeros from top to bottom, right? We have no 0, we have 1 0, 2 zeros and 3 zeros, and I'm done with the Gaussian elimination method. So the last values, okay, in other words, the values that I obtained in this step signals me that I'm done with the Gaussian elimination process, since I now have a row echelon matrix. And then, so the elimination process is over. Let's get back to our definition. See, the definition says that we need to first eliminate our matrix, our arbitrary matrix of size m by n, to either row echelon form or reduced row echelon form. And again, you can also continue with the elimination process. As you remember, we can apply also Gauss-Jordan method. And what should I do if I use Gauss-Jordan method? Then, you know, I also need to eliminate the values not only below the pivot positions but also above the pivot positions. They also need to be all equal to zeros, and all the pivotal positions should be 1, right? If I applied Gauss-Jordan method, then I would have had some kind of matrix in that form, which is called, as you all remember, reduced row echelon form. But this means, in other words, this requires additional cost of computation, right? We don't want to have additional computational cost in this case, because I will obtain the same rank, and the value of rank is not changed depending on the method I use. So the rank is the same. Okay, now, since I completed this elimination process, now I check to see what the value is. Okay, I will either look at the non-zero rows, in other words, I count the number of non-zero rows, or the number of pivotal positions, or the number of basic columns. Okay, and in this case, if you look at here, so how many rows, how many non-zero rows I have here? So the first row is a non-zero row, right? Because at least if there is at least one element which is not equal to 0, then it is a non-zero row. So this is the first one. And the second row also a non-zero row. And the third row is also a non-zero row. And the fourth one is also a non-zero row. You know, if it is a non-zero row, then it must have all of its values equal to 0. So I should have a row which has only zeros. But there is no row in this elimination, after this elimination process, as we see, right? So all the rows are non-zeros, and if I count them, I have 4 non-zero rows, which means that the value, in other words, the rank of A, right, we were looking for the rank of given matrix A, and this is equal to 4. Okay. And another way to look at that is look at the pivot positions. So how many pivots I have with respect to this matrix? Okay. So I count the pivotal positions, and the pivot is that the number of elements which is not the first actually entry, the leading entry, which is not equal to 0 in each non-zero row. And we have only non-zero rows in this matrix, so I have the first pivotal position here, I have the second pivotal position here, because -3 is the leading entry in the second row, and the second row is a non-zero row, and 1 is the leading entry in the third row, because third row is a non-zero row, and 1 is the first element which is not equal to 0, and 11/3 is the fourth pivotal positions. In other words, if I count the number of pivot elements or the pivotal positions, it is still the same. It's again equal to what? It's again equal to 4. Well, this should happen, of course, right? This must happen because the rank of A is unique. So if we are finding the rank of the same matrix, doesn't matter which method or technique we use, we need to obtain the same result. And another way, we look at the number of basic columns, right? And the basic columns are what? And the basic columns are the columns that contain the pivot positions or the pivotal elements, right? So we have 4 pivots, which means we have 4 basic columns, because as you see, I circled in black, these are the columns that include the pivot positions or pivotal elements, right? So we have 4 basic columns, and again it is equal to 4, right? So the rank of this matrix is equal to 4. Alright guys, so in this example we see how we can find the rank of a given arbitrary matrix, right, of size n by n. Okay, let's do another example. Let's make sure that we really understand to find the rank of a given matrix. And also I will make some key observations about finding the rank of a given matrix after showing you how to find the rank of this matrix. Okay, now suppose I am given a matrix like this time in this example. Say 1, 1, okay, and say 2, 3, 2, 3, and say 3, 6, -1, 4, right, and say 2, 1, okay. Now suppose this is the new matrix given us, and what are we required to do here is just find the rank of this matrix, okay, and say, let's give a name to this matrix, okay, let's just put a label, say it is B, and find the rank B. Okay, the question is this: let's find the rank of this given matrix, namely B. Okay, and let's look at the solution. Then, okay, now I have a different matrix, and what is the size here? So we have 5 rows and we have 2 columns, right? So we have a 5 by 2 matrix, and let's see what the rank is going to be. Okay, so what should I do? Again, the strategy is the same. I need to reduce this matrix either to row echelon form or reduced row echelon form. Okay, so I need to first start with picking the method I need to follow. Gaussian elimination or Gauss-Jordan, doesn't matter. I will find the same value. Okay, say again, for the simplicity, I use Gaussian elimination method. Then what is the very first pivot element? I look at the first row in the given matrix, so 1 is the pivot position, right, in the first non-zero row, which is row number 1. So I need to eliminate the values below it. So the values that I just circled in black should all be eliminated. I need to make them zeros. How can I do that? Again, I apply Gaussian elimination method, so I need to replace both rows below the first pivot positions, right? For instance, I need to replace R2 by R2 plus minus 2 times R1. And for the row 3, again, what should I do? I must replace R3 by R3 plus minus 3 times R1, right? I decide the coefficients of the rows depending on what is given to me, right? For instance, since I need to make this 3 is equal to 0, then how can I do that? The only possibility is that I need to multiply the first row by minus 3 and add it to row 3, so I get 0 here, right? And the same thing holds for the other rows. So here there is minus 1. So if I add row 1 and row 4, then I'm done, right? I reach to my goal. So for the fourth row, I replace R4 by R4 plus R1. In other words, 1 times R1, right? I don't write it here because there is 1 here, you know. 1 times R1 is equal to R1, so there is no need to write it down here explicitly. But just let you know, okay. And R5, right? I replace R5 by, again, R5, fifth row, okay, fifth row, plus minus 2 times R1. Okay, here's the thing. And the new matrix we obtain here becomes, let's see what it becomes. It's 1 1, no change in the first row, and 0 1 in the second row, 0 3 in the third row, 0 5 in the fourth row, and 0 minus 1 in the last row as desired. You see now I have eliminated the values below the first pivot position, and I continue with Gaussian elimination process. Now what I should do, I check to see the second pivot element. So I move one step downwards and pass to the second row and see that this is our new pivotal positions, right? 1 in the second row is the first non-zero element in this non-zero row. So this is my second pivot position, and what should I do? I need to eliminate the values right below the second pivot element as usual, right? So in other words, I need to replace row 3, row 4 and row 5 by something else. For instance, for the third row, I need to replace row 3 by minus 3 times row 2. And for the row 4, right, I need to replace row 4 by row 4 plus, this time, minus 5 row 2, right? Because this yields that value 0. Well, sorry, right. This is row 2. And for the row 5, again, this is simple. Just I add row 2 and row 5. Okay. So row 5 plus row 2 will give me the desired result. And then after performing these elementary row operations, our new matrix becomes what? Let's see what we have or what we obtained. Okay, so we have 1 1 again in the first row, 0 1 in the second row, and look at this. Now 0 0, they are all equal to 0, right? See, 0 and 0. Alright, so now am I done with the Gaussian elimination process? The only answer is that yes, I'm done, because now look at this. I have 1 0 here, and if we have a 0 row, these 0 rows must be below all other rows. This is the rule for Gaussian elimination method. In other words, this signals that we're done with the Gaussian elimination method, right? So zeros are again strictly increasing, starting from top to bottom row, right? In the first row we don't have any zero, in the second row we have 1 0, and in the remaining of the rows we have all the values zeros, and these are just 0 rows but nothing. So 0 rows must be below all other non-zero rows. So which means that we're done with the Gaussian elimination method, since our matrix now in row echelon form. Alright then, we are ready to find the rank. And what is the rank of this matrix? Well, I count the number of non-zero rows and how many non-zero rows I have right now. So the first row is a non-zero row, right? And the second row again is a non-zero row. So we have 2 non-zero rows, but we have 3 zero rows. We don't count them. So rank of matrix B, well, that's the name of the matrix, is equal to 2, since we have 2 non-zero rows in that. Another way to look at that, how many pivot positions we have. We have the first pivot position in the first row, and we have the second pivot position in the second row, and no other pivot position. Why? Because the remaining rows below the second pivot position are all zeros. So there is no leading entry below the second row. And again, since we have 2 pivot positions, rank is equal to 2. And if we count the number of basic columns, again, basic columns are the columns that contain the pivotal elements. So we have 2 pivot elements and we have 2 columns, right? We have 2 columns. So again, we have 2 basic columns, and rank is equal to 2, no matter what we use. So rank should be the same. Okay then. Now we know what the rank is, and we also know how we can find the rank of any given arbitrary matrix. Before completing this lecture, I would like to also point out one more thing. In other words, let's make some key observations. Okay, here's the thing. Since the number of non-zero rows is the rank of that matrix, okay, so what is the largest possible value of a rank that we can find? Suppose we are given an m by n matrix, then what is the largest value? So suppose we are given any arbitrary m by n matrix. Okay, here is the thing. After we eliminate this matrix to either row echelon form or reduced row echelon form, doesn't matter which one we use, then the thing is we count the number of non-zero rows, right? So how many rows we have? We have m rows. So what is the possible value? What is the actually largest possible value for the number of non-zero rows after we are done with the elimination process? It is m, right? It can't exceed the number m, because m is the number of rows in total, and the number of non-zero rows shouldn't exceed this number. How about if I want to count the number of basic columns which contain the pivotal elements? Well then, we have n columns in the beginning. So after we are done with the elimination process, we will still have n columns. So there would be no change on either the number of rows or the columns, right? So what is the largest possible value for the number of basic columns? Well, it should be no more than n. The largest possible value is n. And then what can we say? So if m is less than n, right? If m is less than n, then the rank shouldn't exceed the value of m, right? The largest value that is possible for the rank to be is m. Because if it should exceed, then it means that, you know, if you have 4 rows, you found the rank 5. Is it plausible? No, it is not plausible at all, because we don't have 5 rows, right? We only have 4 rows, so the rank shouldn't pass that value. And the same thing is satisfied for this situation as well. If n is less than m, then the largest possible value that rank of this matrix can take shouldn't exceed the value of n, right? The largest value should be n. In other words, which value we pick? We pick the minimum one, right? We pick the minimum one. So minimum of m and n. So the rank of this arbitrary size matrix shouldn't exceed the value of the minimum of this m and n, right? In other words, if we have a 6 by 3 matrix, then which means we have 6 rows and 3 columns, right? But the largest possible value for rank shouldn't exceed 3, because if it passes the value 3, suppose if it is 4, then it is not plausible at all. It is not possible, right? It is not possible to find rank 4, because the number of basic columns at most could be 3. This is a key observation that we can make before completing this lecture, and I would like to point that out clearly, and hopefully that would be usable. Alright guys, this is what I can say about rank for the time being, and I believe that we now know what the definition of rank is and how we can compute or find the rank of given any arbitrary matrix, and how can we conclude, okay, if we are given an arbitrary matrix. Actually, we know the range that a rank can take, right? We at least know what is the possible largest value. It shouldn't exceed that value. So we should be careful about that. Alright guys, rank is a very important topic, especially when we are dealing with a special case of systems of linear equations, what we call as homogeneous systems. And for solving a homogeneous system, we need to find kind of the rank of a matrix, as well as we need to find the basic columns and non-basic columns. And actually now we're done with the rank part, and we will continue in the next lecture with how we can find the basic or non-basic columns and how we can use them. So there would be an important property that we will be using related to that concept. And see you in the next lecture. Until then, have fun guys.